Hi, and welcome to Weapons of Math Instruction. This is the fifth in our series of 7 videos in celebration of Pi Day. If you missed the other 4 videos, you can check them out on my YouTube channel or my Facebook page. In this video, we're going to look at one of the most famous properties of pi, which is the fact that it's an irrational number. You may have seen the meme in which the number pi tells the number I to get real, and I shoots back, be rational, and whoop, hey, there it is. Before I get to the irrationality of pi, I want to talk for a bit on what it means for a number to be rational. We begin by introducing the set of integers, which we denote using the letter z. So the set of integers contains all the whole numbers and their negatives. The ... dots at either end indicates that the pattern implied by the listed elements continues forever in both directions. Next, we introduce the set of rational numbers denoted by the letter q. So the set of rational numbers is a set of all numbers that can be expressed as a ratio of 2 integers. Another word for ratio is quotient, and this q stands for quotient. So when you see the word rational in this context, think ratio or quotient. Now, unlike the integers, there's no simple way to list out the rational numbers, so instead we use what's known as set builder notation. We start by specifying an arbitrary element of the set, p over q. Then after the colon, which is read as such that, we specify conditions for set membership. So the rational numbers, q, are the set of all numbers of the form p over q such that p and q are integers and q is not 0. This last condition is included because division by 0 is illegal in mathematics. And here's an interesting property of q. The decimal expansion of every rational number either terminates or repeats. What do I mean by that? We'll give a couple examples. So 3/4 is a rational number. It's the integer 3 over the integer 4. And its decimal expansion is 0.75. It terminates at the 5. There are no more digits in the expansion. Another example of a rational number is 1/7. It's the integer 1 over the integer 7. Now this decimal expansion does not terminate, but there is a block of digits that gets repeated over and over, 142857, and so we put a bar over that block to indicate its repetition. In this segment, I want to talk about the real numbers, which include the rational numbers. The set of real numbers R, together with the operations of addition and multiplication, can be defined in terms of its properties as a complete ordered field. Now, if this were a rigorous course in real analysis, we'd spend quite a bit of time constructing the reals from the rationals. But that's a bit outside the scope of this Pi Day project, so we won't go there. But I will say a few words about the 3 defining properties of R, complete ordered field. So first, R, when endowed with addition and multiplication, is a field. Addition and multiplication are defined such that the following properties hold for all elements x, y, z in the reals. And these properties are commutative, associative, identity, and inverse. And there's a version of each property for addition and multiplication, so we're going to organize them into a table. The commutative property of addition says that you can move or commute the terms in a sum without affecting the value of the sum. Likewise, the factors in a product can be commuted without affecting the value of the product. The associative property of addition says that you can change the way in which you group or associate the terms in a sum without affecting its value. And the multiplicative version says that the value of a product is unaffected by the grouping of the factors in the product. The additive identity element is the only element that, when added to x, returns x. In R, the additive identity is 0. Likewise, the multiplicative identity element is the only element that, when multiplied by x, returns x. In R, the multiplicative identity is 1. For each x, there's a unique element of R called the additive inverse of x, such that x plus its additive inverse gives the additive identity. We denote the additive inverse of x as negative x. And for each x except x equals 0, there's a unique element of R called the multiplicative inverse of x, such that x times its multiplicative inverse gives the multiplicative identity. We denote the multiplicative inverse of x as x to the negative 1 power. Now at this point, it looks like addition and multiplication are completely separate and have nothing to do with each other. So how do you deal with expressions that have both operations in them? That's where the distributive property comes in. This multiplication by x here distributes over the addition of y and z here to give x times y plus x times z. The second defining property of the field of real numbers is that it is ordered. So let x, y, and z be elements of R. We can define a relation called less than or equal to such that the following properties hold. 1. Either x is less than or equal to y, or y is less than or equal to x. One of those two has to be true. If x is less than or equal to y, and y is less than or equal to x, then x equals y. If x is less than or equal to y, and y is less than or equal to z, then x must be less than or equal to z. That's called the transitive property for less than or equal to. And if x is less than or equal to y, then you could add any real number z to both sides of the inequality, and the inequality still holds true. And finally, if x is less than or equal to y, and 0 is less than or equal to z, so z is not negative, then we can multiply both sides of this inequality by z, and it still holds true. And the third defining property of the real numbers is that they are complete. This means that there are no gaps in R. So we can represent R with a continuous line like this. Every point on the line corresponds to a real number, and every real number has a location on the line. And lest you forget what this video is all about, I've shown our buddy pi here on the real number line. Okay, now that I got all the background info out of the way on the integers, rationals, and reals, it's time to break out the pi. Pi is a real number. It can be located on the real number line, as you saw at the end of the last segment. However, it's not a rational number. And that's just what it means to be an irrational number, a real number that is not rational. So we cannot find two integers p and q such that pi equals p over q. Those two integers just don't exist. This also means that the decimal expansion of pi never terminates and never repeats. The digits just appear randomly. The number I, which admonishes pi to be rational in the opening meme, is not even a real number. It's a square root of -1. Rather, it belongs to the imaginary numbers and also to the complex numbers. But since we're celebrating Pi Day and not I Day, that's all I'll say about this little fella. There are many proofs of the irrationality of pi, and I'm going to present a 1947 proof by a mathematician named Ivan Niven. He called his paper a simple proof that pi is irrational. And indeed, his elegant proof all fits on one side of one page. But that's only because he didn't show all of his work, and he left a lot of details for the reader to work out. I will be filling in all of those details here. One reason that I chose this proof is that it's a proof by contradiction, which is a really nifty method of reasoning in mathematics. In such a proof, one assumes the negation of the proposition P that one wants to prove. In this case, P is that pi is not rational. And so not P is that pi is rational, and this is what we'll assume. Then what you do is you derive a contradiction from the negation of P. And finally conclude that not P is false, and therefore P is true. This is also called indirect proof. But it is every bit as deductively valid as direct proof. And here's a trigger warning. This proof requires a pretty solid understanding of Calculus 1, but no more than that. If you're not feeling very mathy and choose not to continue, I certainly won't hold it against you. But to the intrepid viewer who is just dying to see the proof, let's get to it. So before we get started on the proof, Niven assumes that there exist two positive integers a and b such that pi equals a over b. So he's assuming that pi is rational. To construct his proof, he defines two polynomial functions, f of x and capital F of x, each of which we will discuss below. They each contain an arbitrary positive integer n. So the first function, f of x, is a polynomial function of degree 2n. You get n powers of x from here, and n more powers of x from here. The second function, capital F of x, is also a polynomial function. It's defined in terms of the derivatives of little f. These superscripted numbers are orders of derivatives. So this is the second derivative, this is the fourth derivative, this is the 2nth derivative. And the 2nth derivative is the highest order non-zero derivative of f, because again, f is a polynomial of degree 2n. Now, we're going to lay down some groundwork before we start the proof, because I don't want the reasoning of the proof to be obscured with a bunch of messy details. And the details do get messy. So I'm going to rewrite f of x using the binomial theorem. So x to the n and n factorial just come down out here. And this summation is the binomial expansion of a minus bx to the n. Then I'll rearrange the factors of the coefficient of xj in these brackets here. Now the exact form of these factors doesn't matter. The only thing that does matter for the proof is that this entire thing in brackets is an integer. So I'll rename it Cj to simplify matters. In fact, Niven's proof largely hinges on the coefficients of the function capital F being integers. So here I've labeled the coefficient in brackets as Cj, and I've brought the n factorial and x to the n inside the sum. Now note, capital F is expressed in terms of arbitrary derivatives of little f. So I'm going to want to obtain an expression for the kth derivative of little f. And there are two cases that I have to consider. The first case is the case where 0 is less than or equal to k, which is less than n. So here, I'm about to let the kth derivative operator act on f. And when I do that, the exponent multiplies the coefficient and gets reduced by 1, and this happens k times. So we have this collection of k factors here. And the power of x has been reduced by k. Note that no term in the kth derivative will be constant in this case because n is bigger than k. Now once again, we don't care about the particular form of these coefficients. All we care about is that they're integers. So this whole mess from Cj all the way down to j plus n minus k plus 1, I'm just going to call that dj and note that it's an integer. And the kth derivative cleans up like this. The second case is where k is between n and 2n. So once again, I'll let the kth derivative operator act on f. This time, k is large enough so that the derivatives of some of these terms will be 0. To get rid of those 0 terms, we'll start the sum at k minus n instead of 0. Other than that, the kth derivative looks the same as it did in case 1. Once again, we'll group these factors together and call them dj, which is an integer. Now this time, the kth derivative will have a constant term. Specifically, when j equals k minus n. So I'm going to pull that term out. And I'm going to group the rest of the terms in a sum that starts at j equals k minus n plus 1. Now I'm going to prove a series of 4 lemmas. What's a lemma? A lemma is an intermediate result that needs to be proven on the way to the main result, which is called a theorem. Lemmas help streamline the proofs of theorems. So lemma 1 is that capital F of 0 is an integer. Proof. We're going to show this by looking at the kth derivative of 0. And again, there are two cases to consider. So case 1, k is between 0 and n. And here is our derivative that we came up with on the previous slide, and I've plugged 0 into it. There are no constant terms in this derivative. Every term has an x. So the derivative is exactly 0, which is of course an integer. And case 2 is where k is between n and 2n. And I'm going to plug 0 into our expression for the derivative on the previous slide. Every term in this sum has an x. So this whole thing is 0. And so fk of 0 in this case is equal to the constant term k factorial over n factorial. And when k is bigger than n, or at least equal to n, this is always an integer. Now, since the kth derivative at 0 is an integer for all possible k, it follows that capital F of 0 is an integer as well, because capital F of 0 is just a linear combination of these kth derivatives. Lemma 2. Capital F of pi is an integer. Now remember, this is important. Pi equals the rational number a over b by assumption. So for the proof, we're going to show this by examining a slick little transformation property of little f. we're going to see what happens when we compute f of pi minus x, which by assumption is f of a over b minus x. So, f of pi minus x equals f of a over b minus x. And here, I've substituted a over b minus x in for x into the function little f. Here I've done some simplification. I've combined these two with a common denominator right here. And I've done a little bit of algebra in here to get this. Now, here I have b to the n, and here I have b to the n in the denominator. Those two are going to cancel, and I get this, but that's just little f of x. So the transformation property is that f of pi minus x equals f of x. Now by the chain rule, if I calculate the kth derivative, I find that fk of x equals negative 1 to the k times the kth derivative of pi minus x. Now, plug in x equals pi. The kth derivative at pi equals negative 1 to the k times the kth derivative at 0. But in lemma 1, we learned that the kth derivative at 0 is an integer. Multiplying an integer by plus or minus 1 does not change the fact that you have an integer. So fk of pi is an integer, and it follows that f of pi is an integer as well. That proves lemma 2. Moving on, lemma 3. Capital F double prime of x plus capital F of x equals little f of x. The proof is straightforward. We start by writing down capital F of x. Then we take the second derivative. When we do that, all these derivatives get pushed up by 2. We don't bother with the derivative of this because it's 0. Remember, little f is a polynomial of degree 2n. Now you can see that if we add these two together, these terms all cancel out except for this one. So we'll go ahead and do that. That proves lemma 3. Lemma 4. The derivative of f prime of x sine of x minus f of x cos x equals little f of x sine x. The proof is a straightforward application of the product rule from calculus. So when I take the derivative of the first product, I get f double prime times sine plus f prime times cosine. When I take the derivative of the second product, I get f times sine minus f prime times cosine. And you can see that the second and fourth terms cancel out. And then if we take a look at this, we see we can factor out the sine of x, and we're left with f double prime plus f. But that's just little f by lemma 3. So that proves lemma 4. Okay, let's get to the main result. Consider this integral from 0 to pi of f of x sine of x dx. By lemma 4, the integrand is equal to the derivative of this function in parentheses. Now we're integrating a derivative, which is easy. We just get what's in parentheses. So here, I've applied the fundamental theorem of calculus. And I simplify to get f of pi plus f of 0. By lemmas 1 and 2, these are integers, and so their sum is as well. So this integral is integer valued. But check this out. In the integral, x is between 0 and pi by assumption is a over b. So a minus bx is between 0 and a. Multiplying these inequalities together, I get that x times a minus bx sits between 0 and pi a. Now, in case it's not clear what I'm doing, I'm trying to build the integrand in the middle member so that I can place bounds on it. So here, I raise all three members to the nth power. And here, I divide by n factorial. So now I've got f of x in the middle member. And when x is between 0 and pi, the sine of x is between 0 and 1, so I can include that without changing the bounds. So, on the open interval from 0 to pi, the integrand is positive, and it's bounded above by pi a to the n over n factorial. We're almost home. We see now that the integral has to satisfy this inequality. On the right, it's bounded above by the upper bound of the integrand times the width of the interval of integration, which is pi. And on the left, we see that the integral has to be positive. So not only is the integral integer valued, its value has to be a positive integer. But as n grows arbitrarily large, the upper bound of the integral grows arbitrarily small. This is because the exponential pi a to the n does not grow nearly as fast as the factorial in the denominator. But, since the integral is positive integer valued, this is a contradiction, because there is no arbitrarily small positive integer. The smallest positive integer is 1. So our assumption that pi is rational must be wrong. Therefore, pi is irrational. This completes the proof. Thanks for watching, and tune in to the next video for another bite of pie. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.